Any questions? All right. Yesterday, there was some student came to my office, and they had a little bit difficulty to understand the relative and respect to the ground. And and I'm going to put some problem in the blackboard, and we solve the problem together, and then hopefully you understand. Of course, I solved one problem already for you, relative and not relative, and I was hoping that you understand that. But that student showed me that maybe I should elaborate a little more. All right, so let's say that you do have a cart, and this is a cart, maybe a robot, and this robot is going with a constant velocity v0 and with constant acceleration a0 maybe, or at this time. And this robot has some arm, and at this instance this angle is a 45 degree, and then we do have another arm that is basically moving here, and let's say the length of this arm is A, the length of this arm is B, and at this instance this angle is 30 degree, and this is rotating with angular velocity omega 1 and angular velocity omega dot 1, and both of them respect to the ground. And what that means, respect to the ground. So that means that basically if you do have this arm, and this arm is going with a theta, and you can say that basically if this is your theta, and it's basically going in this direction, and this direction never change. So that is basically respect to the ground. So both of them are respect to the ground. That means that you are judging the orientation of this one respect to the fixed line, respect to the ground, respect to this line, for example, and you say that's omega and omega dot. How is the theta is changing? So now you can also say that this arm, is also rotating respect to the ground, and this is a point P, for example, and this arm is also going in this direction, omega 2 and omega dot 2. So both of these things also respect to ground. What that means, you always judge the angle respect to horizontal line. No matter where it is, you always judge respect to horizontal line. So that is a horizontal line. You always judge respect to this line. So if I ask you what is the velocity of point P, for example, what's the acceleration of point P? So now you do have main reference frame here, x, y, z. Then you can attach another auxiliary reference frame here, x1, y1, z1. Or we can call this an xyz here. Let's put the xyz here, so it would be correct. And then x1, y1, z1. You can attach another auxiliary reference frame here, x2, y2, z2. And we said that if you do have you would like to have velocity at point P respect to point O, let's call it A, B. So you can say velocity at point P respect to, first you go from this coordinate to this coordinate, or you can go from this point and so forth. You can say velocity of point P respect to x1, y1, z1 is equal to the velocity of point B respect to x1, y1, z1 plus velocity of the P respect to x2, y2, z2 plus omega times rho x2, y2, z2. So you go from this coordinate to this coordinate, and then you go from this coordinate to this coordinate. That's auxiliary coordinate system. Velocity of point P respect to the x1, x2, y2, z2 that we are interested, this velocity is simply r omega, and omega is basically omega number 2, and the velocity is simply projection here. So that is basically, you can say that velocity is equal to b omega 2, b omega 2, that's this velocity, b omega 2, and the lines are mutually perpendicular. This angle is also 30 degrees, and so you can say that is equal to minus sine theta j plus cosine theta k. And of course, at this instance, all of these things are the same. Now, what is this term? Velocity of point B respect to the x1, y1, z1, again is r omega or r theta dot, and that velocity is in this direction, normal to here, and that is that velocity, and it's going in that direction. Again, these angles are mutually perpendicular, so this is perpendicular to this, and this is perpendicular to that. That's also 45 degrees. So you can say that this velocity is simply equal to a omega 1, that's r omega, and the angle is here, that would be sine theta, sine 45 j plus cosine 45 k. The last term is omega times rho x2, y2, z2, and that this omega is that your auxiliary reference frame is being twisted. In this case, auxiliary reference frame is all the time never rotates, because you judge this one respect to this coordinate system is respect to ground. So your auxiliary reference frame, it always stays horizontal. It never rotates because it's respect to ground, and that means that you are judging the direction of this one respect to this fixed coordinate system type situation. It never rotates. So this doesn't exist. Doesn't exist. Now let's change the problem. So this term is equal to 0 because both of this velocity is respect to ground. That means that this auxiliary coordinate system that is attached here, even if this goes up, but the direction of this auxiliary reference frame never change because you are judging the rotation of this one respect to the fixed type situation. Now, if I had said this time change the problem, rather than saying respect to the ground, I said omega 2 and omega dot 2 is respect to the arm, respect to arm. So this time is the same problem, but this time instead of saying omega 2 and omega dot 2 respect to the ground, we said respect to the arm. So that means that you have to judge the angle of that arm respect to the other arm. It's not respect to the ground anymore. So this time your auxiliary reference frame is attached to this arm. That is basically, you can call it x1, y1, z1, or whatever. You can say y1, z1, and x1. So this one, you can say that my auxiliary reference frame is attached to the arm, and you are judging the direction of this one respect to the arm. So that's two different things. That's two different things. This one, omega 2, is relative to the arm. So you have to say, where is the arm? And I'm judging always the angle of this line respect to the arm, and that's my arm, and that's angle that you have to judge. That's angle. So in this case, you have to say, okay, what's my velocity again? So you have to say, at this instance. At this instance. So you can say, no problem, velocity of the point P respect to x1, y1, z1, which is still here. You can say velocity at point B, and that's still r omega. That's still this velocity. That has nothing to do with the arm. Has nothing to do with r velocity. That is still is a omega 1 sine 45j, and this time we call it capital J. That's we call it capital J. So you understand that's a little bit different. Plus cosine 45 capital K. Now you said velocity at point P respect to x1. No, this is omega. So that is again at this instance the velocity is b omega 2, and the direction is here, and that's not a problem, but that's relative. So you can say b omega 2, and that's still minus sine 45 minus sine theta, or which is at this instance sine 30 j plus cosine 30k. But this time your auxiliary reference frame is being twisted, because the second arm is respect to the rotation respect to the other arm. So this time you cannot say that this term is 0. So this term has and that is being twisted by omega number 1. So that's omega number 1 I, because the rotation is coming out of the page, times, and the rho would be equal to b cosine 30j, b sine 30k, b cosine 30j plus b sine 30k. So this time is no longer 0, no longer 0, and you do have additional. So in reality, if you look at this problem, and of course once you find here, you can go from here to the fix, and you can find what's the velocity again. In reality, what you are doing, you are saying that this is my arm here. If you are fixing respect to the ground, then this is a method of judgment. That is basically you define how is this angle is changing respect to the ground. And all the time, this is as if, even if this goes up, all the time you're referencing like that. So that's respect to the ground. Respect to ground. And you always keep this one. Even if this one rotating next time it comes here, you still make a judgment that this is angle. You still make a judgment. Even if this comes here, you still make a judgment that this is angle. So you make a judgment respect to the fixed coordinate. It never rotates. Even this one is rotating, but this auxiliary somehow doesn't rotate, because you are judging the other one respect to the ground. If you are talking about relative, then you have to say, I have to have my method of judgment is based on this coordinate. Based on this coordinate. What is this angle? And if my arm is here, no, it is more than 30 degree plus or theta plus rotation of that. So now you are judging the theta of this one plus this one is basically the lines are mutually perpendicular. So this is one angle, theta 1, and this is another angle. So theta 1 plus rotation. So you can say this angle is phi, and this angle, let's see, the lines are mutually perpendicular. This one is a theta 1, and this angle is a phi. So your angular velocity, as you see, when you are talking about relative, is a summation of these two angles, because it's a relative. So you have to make sure when we talk about relative That means that you judge this angle respect to this angle. If I say respect to the ground, no matter where it is going, always you put horizontal and never rotates, as if it is a fixed coordinate system, because it's respect to the ground. And the same thing when you go to the acceleration. If everything is respect to the ground for this one, then you can say my auxiliary reference frame never rotate. Even this one is rotating, but somehow it maintains its orientation. So in order to be you have to pay attention to the statement of the problem. Does it say respect to the ground, or does it say relative? If it says relative, you have to say I have to extend this arm, and I put my coordinate system right here, so then I would be making judgment relative to here, relative to this arm. But if I say respect to the ground, then that's a ground, and all the time I'm fixing respect to the ground as if that never rotates. Even I have other rotation is going. Of course, for this simple problem, you can say what is going on, what is a relative respect to the ground, and what is not respect to ground. And I appreciate next time you be on time to the class. If you are not on time, please don't bother yourself to come to the class. All right? So make sure, because then you do not understand what I'm talking about. And so as you go in the middle of the movie, and then you are lost. So it's very important that you be on time. The same thing that you would like me to be on time, you have to be on time. All right, so now same thing for the acceleration. Now, of course, for certain problem, you would have a hard time to say what is respect to the ground. You make some reference line, how is the rotation? Like the problem that we solved before, if I have, yes, go ahead.
One quick question about this one. So when you're defining NP with respect to x2, y2, z2, and rho with respect to x2, y2, z2, with assuming that the rotation is relative to the first arm, why
Okay.
don't you still define it all as 30 degrees, 30 degrees? Because you change x2, y2, z2. So
Well, at this instance, for example, it's at 30 degree with horizontal floor. At this.
So you can still define everything with respect to big J and K.
Right, you can define it, but that's not a problem. But when you use omega and say, but I'm implementing this one, you have to say whether your rotation is defined respect to the arm or respect to the ground, and then you do that.
Even if the position is defined with respect to the ground, you're still defining position with respect to the ground, but
Position, you can put any coordinate you want. That's not a problem. Position, you can say position respect to this table, position respect to that table. But velocity, when it comes to matter of velocity, you have to say what I'm talking about. Is it velocity respect to the room or velocity respect to the ground? If somebody is outside and he sees my velocity respect to the ground, he doesn't have to worry about the room. He doesn't have to worry about the room. But if you give my information about the velocity in the room plus other thing, then the object, it says that your velocity is different. But I can define my position respect to anywhere that you want, not a problem. That velocity is important. You have to say how it is defined. If this is my arm, and I said this arm is rotating respect to the ground, so you better put references respect to the ground, and this means all the time you're making judgment about this arm respect to the ground. But if you say respect to this one, you better make your judgment respect to this comes here and this comes here. That's relative. So that's two different things. So I'm moving relative to the car. Somebody say maybe you are moving respect to ground, then I don't have to worry about car at all. Because it's respect to ground. It already says respect to ground. So therefore I don't have to make a judgment. Some problem like this is very easy to understand relative and respect to the ground. It's very easy to understand which is relative means relative and what the, and I think I did one problem for you in the class that we had a similar like this, and I solved a problem for you that we have a disk here and then we had an arm here and this arm was pivoted here and this angle was phi. Now if you, and this was rotating, omega. Now, obviously, that phi is respect to the disk. So that's relative. That's relative. This is relative. So you have to put a coordinate system, auxiliary coordinate system like this, relative. And that auxiliary reference frame is being twisted by omega. On the other hand, if you say that, no, I would like to define rotation respect to the ground, that means you put a coordinate system like this. You put a coordinate, and no matter where the disk goes, that arm is respect to the ground. Therefore, auxiliary reference coordinate system never rotates. Never rotates. And in reality, as you see, if this angle is a theta, which theta dot is equal to omega, this angle is phi plus theta. Now you see it's already incorporated. That theta dot, which your auxiliary reference frame is being twisted, is already incorporated in angular velocity, because angular velocity of this arm respect to the ground is not just phi. Angular velocity of this arm respect to the ground is a phi plus. So you could have said if it's relative, you can say your omega total is equal to omega. Let's say that this is capital X, this is capital Y, this is capital Z, omega capital K plus a small phi dot, a small k, and the k comes out of this page. So that's your angular velocity. Your angular velocity is omega capital K, this is capital K, and it's coming out of this page, phi dot, a small k. So this time you do have angular acceleration, and angular acceleration is equal to omega dot. This is constant, no problem. But this a small k, does it change its direction? You do have phi double dot k, but this k never changes direction. It's always perpendicular to the blackboard, and no matter how much rotation you have, that's all you have. That's phi double dot k. Phi double dot k. That's the only thing that you have. Now, if you say respect to the ground, and of course this one, at this k and this k is always in the same direction, that's omega plus phi dot k. Always this k and this k is in the same direction, no problem. If you do the acceleration, as again you see that that's only phi double dot, only phi double dot. K again never change, k never change. That's only phi double dot, which we have. So if you say respect to the ground, then you have to judge this angle. That's respect to the ground. And this angle respect to the ground is equal to theta plus phi. So angular velocity of this one respect to the ground, or the angle, is phi plus theta. And angular velocity is defined phi dot plus theta dot. And theta dot is omega. So you get the same answer, omega plus phi dot. So you have to see how the relative. As I said, in some problem it's easy to say what is respect to ground. In some problem it's difficult. For example, you had a problem like that antenna in the ship. That's a ship, and this antenna. And this is rotating here respect to the ship. The ship itself is doing rotation here respect to ground. And this one is rotating here respect to the ground. So it is very hard for this one to say what is antenna respect to ground. Graphically it would be hard. Here, graphically I can say respect to the ground is this angle. But here, I have a hard time to say what's respect to the ground. So I have to have auxiliary, which is attached to here. And we can say respect to this auxiliary is rotating omega k. Respect to this ship is rotating omega 1 capital I, omega 2 capital J. And my respect to the ground is going to be omega 1 capital I, omega 2 capital J, plus omega 3 small k. But my small k is changing. As a result of this pitching and as a result of this rolling, that small k, which is this antenna, is going to do some pitching. So it can do like this. It can also go like this. So, and it can rotate around. Then when you do the derivatives, this one, all constant. The only thing that k is being rolled. And we said that if you have any vector that is omega that's responsible for the rotation times that vector. So now you have to say this is k dot is equal to omega 1 capital I plus omega 2 capital J times k. And that becomes angular velocity. And then you put it here. Then you multiply by omega 3. And that becomes angular acceleration of that antenna. Here, graphically, it would be hard to show the angle. In contrast to this one that I can show relative nicely, that you can understand this is relative to this arm, relative. Respect to the ground is here all the time, is here. That's not a problem. That's not a problem. You can understand relative and respect to ground. But that one is a little bit difficult to show the angle respect to the ground. If we can show that angle respect to ground, which we have to really go ahead and define some Euler angle, and then based on Euler angle, we can say respect to the ground what is going on. But right now we haven't discussed about Euler angle. Is that clear what I'm talking about? So relative, make sure what it says. If it's a relative and you put auxiliary coordinate system, that means that auxiliary is also being twisted. But if it says respect to the ground, your auxiliary never rotate. Your auxiliary never rotate because you are always judging the direction of this member respect to the ground. And auxiliary in this case is fixed, and fixed in terms of orientation. Did I answer your question, young man? You sure? 100%? So now you understand relative and respect to the ground. All right. Any questions? Any questions? All right. All right. So last time we discussed about the kinetics, and we said that once you have the acceleration of the particle, once you find acceleration of the particle with respect to the ground, then you can make a free body diagram and identify all of the forces, F1, F2, F3, and you can say this is going to be mass times acceleration, and you obtain mass times acceleration of this object. And you can identify all of the forces that's happening to this object, as well as developing the equation of motion, as well as developing in any coordinate system that you are interested. So you identify all the forces, and you identify inertia, and you can obtain all of the forces that's happening to the system, as well as a result of those forces, how the equation of motion or the differential equation that tells you how, for example, theta is evolving, how the x is evolving, and so forth. If you do have an automobile and it's subject to some force, this direction, that direction, you can say how the object is going to move in a space, and you can find the trajectory of that motion. So with that one, let's solve one problem. Let's say that this is a problem we solved in the class last time. Let's say that we have a ring here which is rotating around this axis, with angular velocity omega, and we do have a piece of marble here, which has a mass m. Gravity is acting, and there is no friction, assuming no friction. and there is no friction, frictionless. And this object is also moving in this plane as a result of the external forces that's happening to the system. That is basically your gravity. And of course, you have some torque applying. You are applying some torque that it keep on rotating the system. But we are not going to worry about that part. And we ask you what kind of forces is happening to this mass, and what is the equation of motion? How is the theta is evolving with the time as a result of these things? And of course, you can say at the time equals 0, my system was stationary. At theta was equal, at time equals 0 was theta dot 0. And once you have differential equation, you can solve the problem. So for this problem, the first thing that you have to do, you have to go ahead and say what is the acceleration of this mass. What is this acceleration? And then you identify all of the forces that's happening to this mass, and then hopefully you have equation of motion and other thing that's happening to the system. So you can say that if I make a free body, if I just go ahead and find acceleration of this one, and I can attach an auxiliary reference coordinate system, x, y, z, and know this auxiliary reference system is being twisted. We are not talking about rotation or the rotation of this mass respect to the ground. One is respect to that circle, big circle with the radius r, capital R, and then the whole thing. And our main reference frame is here, x, y, and z. So now you can say, okay, we do have the equation that velocity of point P is equal to r dot O plus velocity of P respect to xyz plus omega times rho xyz. I gave a similar problem to a student for the exam, except I had attached one spring here to this system as well. Maybe we can attach one spring here like this also to the system. But right now, I just add one spring. That's all I did. It wouldn't affect your inertia term, but it affects your forces. Okay? So we have this velocity. And you can say, okay, let's go ahead and this velocity, and especially when we later on we use analytical dynamic, you need the velocity because we go by Lagrangian or Hamiltonian principle, then we use velocity. So you can say velocity of point P, which is this point P, r dot O is equal to 0. Velocity of this point respect to this coordinate system is r theta dot e theta. And of course, e theta is tangent to this circle at different time is different position. But at this instance, you can say is in the plane of the capital X and Y, capital X and Y. So because we put X, Y, Z, and Z is normal to the blackboard. So you can say at this instance, that is r theta dot. And the direction of that one, we can call it e theta, which you can decompose it in the I and J direction if you want. We don't have to. E theta. Now my auxiliary reference frame is being twisted. That's omega, and it's going like this, and that's a capital J. And this is RER. So now you have to say what is this, and this becomes r omega and j and er that you have here, and j times er becomes sine theta sine in between, sine pi minus theta, that becomes sine theta, and the direction of that one is in the direction of negative k. So that's sine theta in the direction of negative k. So the velocity point P, respect to main reference frame, is equal to r theta dot e theta minus r omega sine theta k, which k is perpendicular. And it, again, I solved this problem before. This makes sense because when this system goes here, it has some relative velocity r theta dot, and when it goes around the circle, as if you have a ray, it is traversing around the circle, and at this instant it's perpendicular to the blackboard, and the radius of that one is r sine theta, and times omega. Makes sense. If you want acceleration of P respect to main reference frame, then you can say acceleration of that one is r double dot O plus AXYZ plus 2 omega VXYZ plus omega dot times rho XYZ plus omega times omega times rho XYZ. So again, your auxiliary reference frame doesn't go anywhere, so that's 0. Your AXYZ, as if the disk is fixed, and you do have two acceleration. If something going around the circle, you have two acceleration. One is a normal acceleration, one is tangential acceleration, and that is simply r theta dot square in the direction of negative ER and r theta double dot E theta. So this acceleration is r theta double dot E theta minus r theta dot square ER. That's AXYZ. Now my auxiliary reference frame is being twisted, then I have 2 omega capital J based on this coordinate system. My J is up, my K is normal to the blackboard, times VXYZ, and VXYZ is r theta dot E theta. My auxiliary reference frame is not accelerating, therefore forget about that one. Then I have omega times rho XYZ. That is omega J times omega J times RER. So acceleration of point P respect to main reference frame is equal to r theta double dot E theta minus r theta dot square ER 2 omega J times r theta dot and E theta. So this is your E theta, this is your J, and the lines are, this is theta, and so as this one, this is pi over 2 minus theta, and J times E theta again is negative K and cosine theta. So this becomes 2 omega r theta dot cosine theta, and the direction of that one negative K. J times E theta, it becomes perpendicular to the blackboard, times the angle in between, and the angle between is pi over 2 minus theta, and sine of that one becomes cosine, and that's. Then finally you do have omega times r, let's call r omega square, and J times ER, that's your J, that's your ER, the angle in between is pi minus theta, so that becomes sine theta, so this becomes and j times ER is negative I, negative R. J times is negative I. So that becomes j times ER is negative K, negative K. J times ER is negative. So that becomes R omega and sine theta, and j times ER is negative K based on this coordinate system that I have. And j times K is equal to I, capital I. So this becomes equal to minus R omega square sine theta, and the direction of that one is capital I. You can say capital I if you want. So your acceleration respect to main reference frame becomes minus 2 omega r theta dot cosine theta capital K minus 2 omega r theta dot cosine theta capital K, and then you do have minus r omega square sine theta capital I, and this is your main reference frame X. So now you go ahead, you have acceleration. Now you have to go ahead and make a free body diagram. What is going on? What is going on? So if you go ahead and make a free body diagram, this is my particle, and this is my capital X, this is my capital Y, and it's coming out of the page capital Z. I have mg gravity here. I have a reaction N to the surface, which goes through the center of the disk. And then I have another one normal to this one, and in this direction I don't have any friction or anything like that. So I have another force normal to the blackboard, because you do have two contact surfaces. You do have one contact here, one contact here, so you have two contact surfaces basically. And you do have another force normal to the blackboard. We can call it, what do you want to call it? We can call it force Z. So we do have another force in this direction normal to the blackboard. This is normal to the blackboard, Fz. So this is all of the forces that's happening to my system. For the problem that I gave in exam, we had another force from a spring that was coming here. Another force from a spring that was coming here doesn't affect your inertia, doesn't affect your acceleration. So that is not a problem. Now you make another picture, and that is again your XYZ. And that is basically your and for this picture you put all of your inertia. Well, let's see what we have. We have r theta double dot e theta, so we put it back here, mass times r theta double dot. We have r theta dot square, we put another one in this direction, mass times r theta dot square. We have one perpendicular to the page in the direction of K, mass times minus 2 omega r theta dot cosine theta. This is perpendicular. The other two are not perpendicular to the page, is in the plane of the ring. And finally, we have one more acceleration, which is one in this direction, mass times r omega square sine theta. So if you are just interested how is the theta is evolving and what's the differential equation that it tells you how the theta as a function of time is evolving as a result of this rotation. And so if I have something is rotating, that something may evolve. So if I'm rotating something like this, I don't want to hit the monitor. So then theta is evolving, and you are interested to see what is the velocity of this one, theta as a function of time at any time, or if I'm doing something as well as this thing, so is how it is evolving. Then you need the differential equation which relate the theta to the external forces. Your external forces are mg. N and Fz are reaction forces. They are internal. So the one that you are applied to the system, they are called applied forces. The one that you only apply is mg, gravity. But nevertheless, you can go ahead and say summation forces in this direction, in the direction of ER, for this picture must be equal summation forces in ER for this picture. Summation forces in this direction, in the K direction for this picture must be equal summation forces in. So you can also identify the forces. So if I write summation forces, but generally we are interested in the differential equation that tells me how the things are evolving. And this is valid for the particle as well as rigid body. Later on we talk about rigid body. So now you can say, no problem, if I want my n, for example, what is my n? You can say any force in the n direction, in this direction, for this picture, must be equal. So now let's see what we have. We have n in negative ER direction. Let's assume negative ER direction positive. So n minus mg cosine theta. So that becomes all of the forces in the R direction. This angle is a theta. So as this angle is theta, so n minus mg cosine theta. Now you go ahead and for this picture, you look at anything in this direction. Anything in this direction. And hopefully from here you can find, and of course this Fz is normal to the blackboard, so therefore it doesn't have any component in that R direction. So it is normal to the R anyway. That's Fz, doesn't have any component in there. So now you go to this picture. Again, this is normal to the blackboard. You don't have any component. You do have R theta dot. Again, it doesn't have any component in the R direction because this is normal to the R. The only thing that you have is m R theta dot square. And m r omega square sine theta, and you multiply by this angle projection, and this theta, and this pi over 2 minus theta, and cosine of this angle becomes sine square theta. So that is basically, you can find what's n. What's n. And if you know all of those things that you have monitored somehow, and you put some camera and see how is your theta is evolving and how is other thing is evolving, you should be able to find that. If you want Fz, any force in the K direction for this picture must be equal for this picture. The only forces that I have in the K direction is Fz. So Fz for this picture must be equal to m minus 2 omega r theta dot cosine theta. Now if I want to know how is the theta is evolving, I can take the moment of all these forces respect to the center and take the moment of all these forces respect to this, let's call respect to z axis, respect to z. Doesn't make any matter. Whatever you do to this picture, you do to this picture. If you want to know how is your theta is evolving, let's take the moment respect to z axis. Moment of all forces respect to z-axis for both picture. So if you do that, this mg times this distance, it produces mg times r sine theta, and that's in negative k direction. That's mg minus mg r sine theta, negative k. Let's call negative k minus mg r sine theta. This n goes through the z-axis, and this fz is also parallel to z-axis. They do not produce any moment. They do not produce any moment. So the only one that produces moment respect to z-axis is mg times this. This is parallel to z-axis, and this goes through the z-axis. So now you go ahead and take the moment of all of this thing respect to z-axis again. So if you take respect to this z-axis, this goes through the z-axis, does not produce. This produces respect to z-axis mr theta double dot, and that's positive. mr square theta double dot. That is positive. This one is a parallel to z-axis, but this one has moment respect to z-axis, that's negative. mr omega square sine and times r cosine theta. So minus mr omega square sine theta, that's basically that, times r cosine theta. So as you see, you have developed some differential equation, and your differential equation is mr square theta double dot plus mg r minus mr omega square cosine theta times sine theta equal to 0. That's highly nonlinear differential equation. Highly nonlinear differential equation. And that's your differential equation that you have. So very simple, we develop the differential equation by identifying the inertia and identify the forces and put in the two different picture. And one thing that you are interested to develop the equation motion, if I kick this table with external forces, what is the subsequent motion of this one in a space? And you need the differential equation to find that subsequent motion. And that is that differential equation. So while we are here on this one, we may be interested while we are here may be interested that if we do have this ring and this marble is here and we are rotating omega, at what omega this is going to go and become fixed. We may be interested, if you keep on rotating this one, it's like that let me see whether I can take this mouse. If I keep on rotating this one, eventually you may see, okay, you get some angle, fixed angle, and that is a fixed angle. I want maybe interested to see what's that fixed angle based on omega that I'm imposing. What is that fixed angle? If I rotate it faster, of course it gets bigger angle, and if I rotate it very fast, then I may damage the mouse. So I don't want that. All right? then it flies and I may hit you, one of you guys. So the question is that, am I twisting like this? Eventually I get some constant angle. How do I find that? How do I find that? What's the relationship as you are twisting that mouse that I was just presenting to you, and you are rotating it, eventually you may come to a constant angle. How do I find that? How do I find that? Don't close your eyes.
Theta dot and theta double dot and zero.
That's right. When it comes, at some point, it becomes here, and it gets fixed. Then you can say it doesn't change anymore. At that particular omega, your theta is fixed. No theta dot, no theta double dot. So if you would like to consider the position that it gets at certain omega, you can say that at that situation, at this particular omega, it can be this situation. So you can say, I'm looking for the equilibrium position, like that mouse that I was rotating for you. If I rotate it very fast, and you may have done it when you were a little child, you were playing with some toys and you twisted, you say, oh, it comes like this. If you turn it very fast. Have you done that? How many of you have done that? Yeah, I have done that. And if you rotate it very slowly, sluggishly, then you can say maybe it has very small angle. So it has, this is a 2 degree of freedom system. So here, I rotate it like this. That's a little bit easier. Rotate it, rotate it like this. No, I rotate it very fast. What do you see? It comes like that, right? So it depends on a speed, right? It depends on the speed. So that's a question, at what speed, what angle. So you can say, no problem. That's my equation of motion at equilibrium position, or at both my theta dot and theta double dot is equal to what? 0, as he said. So you can go back and put back in this equation, and then if you have you can solve that equation. So you can say that if I put back in the equation, I'm looking for equilibrium position. So now you can say mgr minus mr square omega square cosine theta times sine theta equals 0, and that tells you you could have 3 scenarios. That one scenario is independent of omega, 2 scenario is independent of omega, and 1 scenario depends on omega. So you could have 3 stable position or equilibrium position. We don't want to say stable. So you could have a situation that sine theta is equal to 0. That means theta could be 0 and theta could be equal to pi. So that means that if your marble is here, your marble is here, or your marble is here, and you rotate the system, you could have basically no movement. Theoretically, you could have no movement. So it can stick there and it wouldn't move. You could have one equilibrium position. Obviously, for the pendulum that I just demonstrated for you, it is at some angle, and it's a function of omega. So you do have one situation like this. You have another situation that this is equal to 0. This is equal to 0, and that means mgr minus mr square omega square cosine theta equals 0, or cosine theta is equal, m and m cancel each other, g over r omega square. So you could have, as you see that if the omega gets very large, what happens to cosine theta? When omega gets very large, it becomes what? This becomes 0, and theta becomes how much? Theta becomes how much? 90 degree. 90 degree, like what I demonstrated for you in the class. 90 degree. If you rotate it very fast, eventually this marble may go and become horizontal. Make sense? I just demonstrate for you. In order for you to have some at other than 90 degree, some theta other than 90 degree, what must be your omega? In order to have this situation, your omega has to be certain amount. So your omega has to be what? In order to have another position at some theta, what do you think that omega should be? So well, this number should be less than 1. Less than 1. In order to have this situation, this number has to be less than 1. So your omega has to be greater than a certain amount. You cannot have this situation if omega is less. So you can say G over R omega square must be less than 1, or a speed of your rotation in order to have another angle other than 90 degree, omega has to be greater than G over R. G over R. So that means that as long as you rotate the structure with a speed greater than G over R, then you could have a situation that it obtains some angle like this. And then if you rotate it faster, then it goes get more and more arm. It comes to the equilibrium position. So we can identify the forces that happen to the system. We can also develop differential equation that how is my theta is evolving as a function of the rotation, how is my theta is evolving. We can also find it out at what rotation we would have a fixed theta, fixed. And we find it out at two position, this position and this position. We could have those position, and no matter how fast we rotate it, it can stays there. It could stays there. We could also find that if your speed is this much, omega is greater than h over r, then you could have another position that we can call it equilibrium position, and that equilibrium position can be obtained by this equation, G over R omega square. And this angle depends on your speed that you rotate. If I rotate it very fast, then it becomes horizontal, very fast. If I do it slowly, no, it comes like this, like that. Any questions? All right, now we would like to add a little bit more to this one, So that's my differential equation. And I said, if I rotate it here, let's say that I put my marble here, forget about this one, and I keep on rotating. Theoretically, the marble can stay there without movement. Theoretically, it can move at that location and stays there, theoretically. No problem. How about if I just go ahead and disturb it a little bit? Just disturb it, a small disturbance. If I put a small disturbance to this location, around this location, what's going to happen? As I said, you do have a situation that the marble can be here, and we can put it like this. For this problem, we could have 3 equilibrium position. We can put on this one omega, and we could have here theta. we said that you do have 3 equilibrium position. One is theta equal to 0 and is independent of omega. Is independent of omega. Another one that we could have is at theta equal to pi. That's another one, pi. And the third one is cosine theta is g over r omega squared, but this only exists is if omega is greater than a square root of g over r. Omega is greater. So this is only exists at a square root of g over r, and as your omega is increases, then it approaches to pi over 2, and the equation of that line, it becomes like this. Cosine theta is g over r omega squared, and that is basically, it goes asymptotically approach to the pi over 2. So that is yet another equilibrium position. But this equilibrium position does not exist if you rotate it sluggishly. If you rotate it sluggishly, this equilibrium position does not exist. It only exists if your speed is greater than square root of g over r. Now we go ahead and talk about another thing which we call stability. Stability. Now what happens? What happens if my theta that's here and is sticking there and is equilibrium, somehow somebody goes and disturb it around that equilibrium position. Equilibrium position. Is it going to come back to the 0 position, or is going to take off as if you are standing in the top of a tall building? And so you are standing in the top of a tall building and you wobble a little bit. Are you going to get killed and you fall down from that tall building to the earth? You produce large displacement, or you simply, you just rock a little bit like a drunk people, and then you will be okay. You will be okay. You wouldn't fall down. The question is, if I disturb this one around that position that supposedly can stays there and is not is independent of omega, is it going to rock back and forth? Or as soon as you put a little bit disturbance, then it's like a buckling. You have a buckling, and if you compress it, no problem. But if you put some lateral motion, is it all of a sudden would like to jump to another situation, or simply say, no problem, I'm going to oscillate a little bit and come back to the... So we would like to talk about that. So you can say, okay, if in that case, if I put my theta disturbance, theta is going to be theta equilibrium plus a small disturbance, and for the and if I just look at the around 0 degree, equilibrium at 0 degree, this becomes 0 for 0 position. Then my theta becomes equal to epsilon. Very small disturbance. And my theta dot becomes epsilon dot. And my theta double dot becomes epsilon double dot. And my sine theta becomes epsilon, and my cosine theta becomes equal to 1. Because I'm talking about epsilon, a small disturbance. And if I just go back and put in this differential equation to see what is happening, to this differential equation to see what is happening, then my equation becomes mr squared epsilon double dot plus mg r minus mr squared omega squared cosine theta becomes equal to 1 and times epsilon. So if I simply go ahead and substitute back in this equation, then we see what's happening here. So what do you understand from this equation? What do you understand from this equation? According to your math background, hopefully you do have math background, if this number is a positive, that means system has oscillatory motion. If this number is negative, that means the system has exponential. So that means that oscillatory is stable, exponential as a function of time is unstable. So as long as this number is positive, that means that your system is stable. So based on this one, that means that mg r minus mr squared omega squared, if it is a positive, that's stable. And in order that to be stable, omega has to be less than, omega squared must be less than g over r. G over r. So that means that up to this omega, up to this speed, you are stable. Up to this. Up to this speed, you are stable because your system would have epsilon as a function. Epsilon is not going to build up more. It's not going to go crazy and exponentially. It's stable. Above this number, then with a little bit disturbance, the marble does not want to stay there. The marble does not want to stay there. And with a little bit disturbance, it starts to move. It starts to go to another location and keep on moving. Keep on moving. And so that is unstable. So as long as your speed that you rotated is less than a square root of g over r, then your marble stays in the bottom of the tank and it wouldn't go anywhere. But if your speed is greater than that, then become unstable because this number becomes negative and your system response becomes exponential. So then it's unstable. And you will get a problem about stability in your exam. So that becomes unstable. Now let's look at the situation for when the marble, let's look at the situation. Let's look at the situation when the marble is in the top of the ring. We had three positions that you could have basically equilibrium position that is stuck there, and you would have a situation. So now let's look at the situation that your marble is here, your marble is here, and you are rotating this one. And we are interested, if we make a disturbance, if you make a small disturbance, what happens? What happens? Is it going to fall down from the cliff, or again, is it stays there and oscillate back and forth, and it comes back to position? What do you think? What do you think? Without solving the problem, what do you think? Is it stable or unstable? Huh? Unstable. Does it depend on omega? Does it depend on the speed? Not. Let's go ahead and see. So another equilibrium position was theta is equal to pi, and now you make it a small disturbance, and theta epsilon. So your theta dot becomes equal to epsilon dot, and your theta double dot becomes epsilon double dot, and your sine theta becomes equal to minus epsilon, and cosine theta becomes -1. So now you put it back in this equation. You put it back in this equation, and mr squared epsilon double dot plus mg r plus mr square omega square, and this cosine theta is negative, negative times negative become positive, and times epsilon, and sine theta is minus epsilon. So as you see in this problem, no matter what's omega, this number is what? Negative. Solution to this differential equation is exponential. So therefore, no matter what's omega, no matter what's your speed, if you put your marble over there and you rotate it, you better believe that it's going to fall down. It's going to fall down. So it's for any speed, it's going to be unstable. So it is unstable for any speed. Unstable. Unstable. So we have another equilibrium position, which is this one, and this exists if your speed is greater than this number. If your speed is less than this number, it wouldn't exist. So it is sluggishly, it stays in top or bottom, doesn't exist. So we would like to discuss about this equilibrium position. Is it stable if I am rotating at certain speed, which is maybe around here, this speed, if I'm rotating here, and no, based on the mathematics, it says that yes, at that speed, the marble can go here and get stuck. Get stuck. Now, if I disturb it a little bit around this here, is it going to take off again and exponentially, or it is stable? What do you think? What do you think, without solving the problem?
Stable.
Mostly stable. Let's go ahead and find it out. Let's go and find it out whether it's stable. So remember that cosine theta in this situation, cosine theta equilibrium was g over r omega square. So now you can go ahead and say, no problem. No problem. And we will solve quite a bit number of the stability problem for different rigid body as well. But this is right now a simple problem. Now you can say, okay, this time again my theta is equal theta equilibrium plus a small epsilon. And my theta dot is going to be epsilon dot, and my theta double dot is going to be epsilon double dot. My sine theta is going to be sine theta equilibrium plus epsilon, and that becomes sine theta equilibrium. Cosine epsilon, that becomes 1 plus cosine theta equilibrium times epsilon. So if you just expand sine theta, becomes sine theta, cosine epsilon, sine equilibrium, something like that. So it becomes sine theta e, if you do not, cosine epsilon plus sine epsilon cosine theta e. This is epsilon, this is equal to 1, then you put it back here, and that's what you have. To elaborate for a graduate course. Cosine theta plus epsilon, cosine theta equilibrium plus epsilon. What is this? Cosine theta equilibrium plus epsilon, do you remember that? Does anybody remember that? Can I expand that one? Cosine? Yes. Cosine, tell me. Cosine theta equilibrium? Cosine epsilon? Minus sine theta equilibrium? Sine epsilon. You agree with that? Okay, that's according to my high school. So this becomes equal to 1. This becomes equal to epsilon. So this becomes cosine theta equilibrium minus epsilon sine theta equilibrium. So now you're all set, and you put it back everything to this differential equation. You put everything to this differential equation. Remember, cosine theta equilibrium is a g over r omega square. Remember that one. So that's the only thing that you want you to remember that. So now if you put everything back in that differential equation, if you put everything back in that differential equation, that becomes mr square epsilon theta double dot, and theta double dot becomes epsilon double dot, plus mgr minus mr square omega square, and cosine theta is equal to cosine theta equilibrium minus epsilon sine theta equilibrium. So that becomes cosine theta equilibrium minus epsilon sine theta equilibrium. That's I put here, cosine theta. Times sine theta, and sine theta is equal to this expression, sine theta equilibrium plus epsilon cosine theta equilibrium. Sine theta equilibrium plus epsilon cosine theta equilibrium. So now let's go ahead and expand this one a little bit. So that becomes mr square epsilon double dot plus mgr minus mr square omega square cosine theta equilibrium minus mr square or plus mr square omega square sine theta equilibrium times epsilon times sine theta equilibrium plus epsilon cosine theta equilibrium. If I simply go ahead and substitute for cosine theta equilibrium is g over r omega square, g over r omega square. If I substitute for the cosine theta, you can clearly see that this term and this term cancel each other. So you can clearly see that if I substitute for the cosine theta and g over r omega square, these two terms cancel each other, and this equation left with mr square epsilon double dot plus mr square omega square sine theta equilibrium. Epsilon sine theta, that becomes sine, another sine theta epsilon, and this epsilon times epsilon becomes second order term compared to the first order term, so forget about that. So that becomes epsilon squared. So these two terms cancel each other, and when you multiply epsilon by this one is okay, that's the first order term. Epsilon by epsilon becomes epsilon squared, that's forget about second order term. That's equal to 0. So as you see again, that this term is positive. No matter what's the omega, as long as omega is greater than square root of g over r. So this term is positive. That means the system is stable. Stable. So if your marble goes to some location at certain omega, and you disturb it a little bit, it doesn't go crazy. It doesn't go off the cliff. So it's stable. We will do some more stability problem for you, much more difficult than this. Right now, this is a very easy one to understand stability, but we will solve more problem for you and talk about stability. And you will get a problem in the exam. Talk about it. You have to develop the equation motion and find where is the equilibrium position, then do the stability analysis. Any question on this problem? Okay. The only thing that you have to do, you have to go home and say, this is a problem that professor solved. I have another problem on this one, stability, which I can, let me see. Yeah, I can solve this one, but this takes time. This will take time. I can do that. Yes, question. Yes.
Can I come up there?
No.
Okay. When you did the small displacement around theta equals pi, for sine, when you got sine theta, how'd you get sine theta equals minus epsilon? Well, I mean, yeah, why is it minus epsilon?
Sine pi plus epsilon. Sine pi plus epsilon.
Yeah, how did you get sine?
That's become minus sine epsilon.
Sine theta equals minus epsilon.
Look at some geometry, some trigonometric function. Trigonometry. This is basically when you do have. I shouldn't talk about this, but when you have sine is defined this length. Okay, so when you come to this point, sine become negative. Okay, so now look at the geometry. This has nothing to do with this course. Okay, look at some trigonometric equivalency, and you will see that sine pi plus epsilon is minus sine epsilon. All right. Any other question? Any other question? All right. So now. So what we said, that if you do have a particle and it's subject to a lot of forces, and this obtains some inertia, and according to Newton's law, is equal to mass times acceleration, or you can say d over dt of mv, and this is called linear momentum. Linear momentum. Linear momentum. D, you can say that forces is equal change of momentum. And your book called this one P. I use different terminology. I don't want to follow exactly what the book is doing. Then it is not my style. But hey, your book called it P, d over dt of P, linear momentum. I like to say mv. Because P, I do not know what the P is, so I make it confused. Linear momentum. So forces, summation of moment, summation of forces is equal to d over dt for a particle is equal change of momentum. Now, if you multiply both sides of this equation, by dr, so if this one displaces dr, and you also displace this one dr, you multiply this one by dr, it is not different equation. You think that you are getting different equation, but it's really from f is equal to ma. There's not different equation. So if you multiply both sides of this equation by dr, that means integration of f dr, you multiply dot product, and you put d over dt of mv dr, and this becomes summation of f dr is equal to d mv times dr dt. You can put the v. And because the v and mv are in the same direction, basically, then you can say this is equal to d 1/2 mv squared. And if you integrate this expression, integration from position 1 to position 2 f dr, it becomes equal to 1/2 mv2 square minus 1/2 mv1 square. And this is called work and energy, or kinetic energy. This is called change of kinetic energy, 1/2 mv square. But this equation really came from Newton's law. So this looks a little bit different equation. Theoretically, you should be able to solve any problem with just Newton's law. But maybe it takes a little bit of time. Maybe it takes a little bit of time. And so that says that the work that is done to the particle from stage 1 to stage 2, FDR, is equal to 1/2 mv2 square minus mv1 square, change of kinetic energy. Now, there are some forces that the work does not depend on the path of the motion. So no matter you go from this position to this position, and this is R1, this is R2 that you have, and no matter what position you go, the work doesn't depend on the path of the motions. In other words, integration of FDR does not depend on the path of the motion. Doesn't. Certain forces are like that. Those forces that it just depends on the end condition, not on the path of the motion, those are called conservative forces. So conservative forces work does not depend on the path of the motion. And those forces are called conservative forces, and the work associated with that one is called potential energy. And from stage 1 to stage 2 is called minus V2 plus V1. And it's called potential energy. Doesn't depend on the path, it just depends on the end condition. Those forces are called conservative forces. So this work that you have here, you can say that if I have conservative forces, and those are called potential energy. So this you can say I can break it down to the two forces, conservative forces and non-conservative. Friction depends on the path of the motion. A spring depends on the end location. How much work is it? Gravity doesn't make how it goes. It depends to the end condition. So those are conservative forces, and those are called, the work associated with those forces called potential energy. So you can say that this one, you can break it down to minus V2 plus V1 plus non-conservative forces, is equal to 1/2 mv2 square minus 1/2 mv1 square. And that's called kinetic energy. So that kinetic energy at stage 2 plus potential energy at stage 2 is equal to kinetic energy at stage 1 plus potential energy at stage 1 plus work of non-conservative, 1 FDR. So you can bring this one to the other side of the equation, and you can take this one to the other side of the equation. That's called potential energy, kinetic energy, and that's basically some problems. Rather than go ahead and make a free body diagram and try to solve the problem like that, you may be able to find quickly, especially if they ask what's the velocity at the end stage. So you don't want to write the differential equation, solve the differential equation over the path of the motion. He's just asking from this location, it jumped to that location. How it jumped in that location, you don't care. If you want the complete history, then you definitely have to write the differential equation. You definitely have to write the differential equation and see the entire path of that train. But if it says the train was here, then he went there, and these are the forces, this is the kings, and so forth. He wants the end condition. He doesn't want in between what's going on. In between, who cares? Then you may just want to write without you don't need to write the differential equation. You simply say, can I use the concept of work and energy? Can I use the concept of work and energy and to get the job done? All right? So let's say that you have a piece of marble, and this piece of marble is here at the distance of, let's say, 10 meters, and this mass is equal to 2 kilograms. Gravity is equal to 10 meters per second square. And this marble is released, and it comes here. It comes here, down. In between, I don't care. We want to know what's the velocity when it gets to the bottom. What velocity got to bottom? And there is no friction, assuming there is no friction. Because if there is a friction, then you have to really know how much is a friction and how much work is done. There is no friction. And you have to know the path, and you have to integrate all of the path. And you can do the work and energy, but you have to know it. Then you may be as well write the differential equation, solve the differential equation to see what is the position, and then at any time, and then you have as a function of time, everything. That you need the differential equation. But if it is asking what is the velocity at this position, then you say no problem. And this force, there is a forces applied here. This force normal to here, and mg is applied here. You do have mg, but this n is normal to the path, and is normal to dr, and therefore it doesn't do any work. The only one that does the work is mg, and mg is basically doesn't depend on the path of the motion. It just depends how it went down, and we can go ahead and see how the gravity does not have to. You can go ahead FDR, put mg times dr, and you can see, well, it's only dz. It's only dz that comes is important. So if you can say this mg, and you multiply this by dr, then you can see that it's multiplied by dz only. And that dz is the only one. Therefore, you can say mg dz or dy. And therefore, you can see that doesn't depend on the path. So this is your dr. This is your mg, and if you multiply mg by dr, like a dot product, then you can see that's the dz dy. So that becomes an integration of mg dy. And so then you can say it's like a potential energy. So potential energy of the gravity is mg times y. And there is no other forces, so you can say for this problem, FDR is equal to 0, T1 is equal to 0, because it's just a start. Potential energy mg times 10 meter, m is equal to 2 kilogram, g is equal to 10 meter per second, and y is equal to 10 meter. Let's put this one 15 meter, so you don't get confused. 15 meter. That's a T1 is 0, V1 is 0, and that's equal T2 is 1/2 mv2 square, and that is equal to 2 kilogram times velocity square. And from here you can say velocity becomes equal to velocity square. That becomes 20 times 15. That becomes 300, a square root of 300 meter per second, which becomes around 17.3 meter per second. All right, why don't we stop here? We continue on this discussion, and next time we talk about impulse and momentum, and we solve some problem, and then we go further on that rigid body.